You're doing quantitative research in healthcare. Most likely, you're going to have to perform a hypothesis test in the end. But you need to know which hypothesis test that will be at the very beginning as you're designing your study, because the type of test relates directly to the data you're collecting. And trust me, you don't want to do an entire study only to find out in the end that you've collected a whole bunch of data that you can't use to test any hypotheses. Without going into a full review of a statistics course, let's look at the common kinds of tests you might be using and how you might determine which one is right for your research. Here's a list of some of the tests that you often see in healthcare research. And this isn't even a comprehensive list. There are many more tests that could be used, but don't panic, because even this is a much longer list than the most common tests. Here I've pared down the list to the most common ones you'll probably be considering for your healthcare research. I'm going to rearrange these tests to try and make it easier to decide which test is the right one for your research. So, I regrouped the tests in a new arrangement. You'll notice that one of the tests, the two-sample t-test, is listed twice, but I'll explain why in a moment. Let's deal with the big question. How do I determine which test is most appropriate for my research? To figure that out, the big question, we're going to ask ourselves three smaller questions about the study we're hoping to do. Question 1. What type of data do you plan to collect? Data can be broken into two classes, categorical and quantitative. Quantitative data are easier to understand. They're usually measurements. Most things you measure about your patients are quantitative data. Height, weight, blood pressure, body temperature, vital capacity, or a pain rating on a scale of 1 to 10. But sometimes, when you're counting something, that's also quantitative data. Let me come back to counting because I have to be a little careful. First, let me define categorical data. Labels, yeses and nos, which relatives had heart disease. These all have basically words as their answers. They're categories, they're categorical data. But often we count how many answers of each type we get when we're using categorical data. Let me give you an example. If I ask a group of people, do you have any siblings, and I count the number who say yes, then really my data is the yes or no answers that they gave me. It's categorical data. I'm just counting the number of subjects in my sample to find the proportion of them who said yes. I'm counting the people. The data is not the counts itself. On the other hand, if I ask people, how many siblings do you have, they could answer 0, 1, 2, or so on, any number. Each data value is now a number, a count. This is quantitative data. When the data itself is a count, each person could be a different number, that's quantitative. When only the subjects are what I'm counting, how many subjects answered with a particular answer, that's categorical data. And I'm determining what proportion of my subjects answered yes or had a parent with heart disease, for example. In healthcare, when you talk about those proportions, you often call them rates. A patient falls rate is a proportion of the patient hours that involved falling, yes or no. A mortality rate is the proportion of the procedures that ended in death. The data is either die or survive, categorical data. All right, so I've separated out our different tests into two groups, categorical and quantitative. It gives us our first major separation. I have my categorical data in the teal background. When I have categorical data, I'm dealing with proportions, and you can see my tests are both about proportions. My other tests all require quantitative data, so I've got the remaining tests in an orange background. If you tried to do any of those tests with categorical data, it wouldn't be possible. In fact, for all of them, except for one, correlation regression, you're comparing means. You can't take the mean of data if it isn't quantitative. All right, here's your second question. Question 2, how many different samples will you have? Or how many different groups will your subjects be in? In a classic experiment, you have a test group and a control group. The test group gets a certain treatment that the control group does not. This is two different groups, two separate samples. In this case, you're most likely comparing the results of one group to the results of the other. But maybe you only have one group. If that's the case, you're most likely comparing the results from that group to some historical number or global value provided by an outside source. Possibly you could have even more than two groups. Maybe you have subjects who get a lot of headaches, and one group takes acetaminophen, one group takes ibuprofen, and the control group takes nothing. You'll also notice I mention in this slide two samples special, or I called it two-ish samples, because you might have two groups of people, or you might have one group of people, but you've taken two separate measurements from those people. Let's look at that situation in a bit more detail. So often you have only one group of people, but we treat it as two sample special because I really have two sets of data. I've given some examples here. Before and after data. In this example, the body weight before and after being put on a diet. Only one sample of people, but you have two samples of data that came from that people. From that group of people. Before and after data is only one example. You can see I've listed other examples where I might be making two measurements from the same group of people. Sometimes I'm comparing those two samples of data. Sometimes I'm just asking, is there a relationship between them? We're going to get back to that in our question 3. Another time you have two samples special is when you actually have two samples, but these samples can be naturally paired. Each person in the first sample goes with a specific person in the second sample. So I have one sample of new mothers, and the other sample is the newborn babies of those mothers. Each baby goes with a specific mother. Each mother goes with a specific baby. In these kinds of two samples specials, you're almost always looking for a relationship between the data collected between the first sample and the data collected from the second. It does happen occasionally that you want to compare and contrast them rather than find a relationship, but that's not nearly as common. Alright, so now I'm separating my tests based on the two questions we've asked. Categorical versus quantitative data, and do I have one sample, two sample special, or three or more samples? So for example, if I have categorical data, and I have one sample, I'm using what's called a one-sample proportion test. With two samples, I'm using a two-sample proportion test. The names are pretty obvious. Just to let you know, if you have more than two samples and you're looking at categorical data, there is another test called a chi-square test. It's not as commonly used in healthcare, but I wanted you to know it exists. When you have quantitative data, we might know what to do already, we might not. If you have quantitative data and you have the two sample special, well, we need to ask ourselves one more question. Question 3. What is the hypothesis test supposed to do? Either it's a comparison of the data, maybe between the groups or from the one group you have to a historic value, or if it's not that, then you're seeking a relationship between the two sets of data. Comparing the data is by far the most common. If I have one sample, I want to know if the results from my one sample are the same or different than the historic or global value previously determined for this type of data. If I have more than one sample, are the values of my sample close to one another or not? In other words, if they are different, is it just because anytime you randomly choose samples you will get slight differences? Or is there difference because there really is something not the same about the populations that each sample came from? Let's take a classic experiment as an example. I use a new laser surgery on the subjects in the test group. I use the traditional surgery on the subjects in the control group, and then I measure the recovery times of the people in both of those groups. I take the mean recovery time of the test group and the mean recovery time of the control group. Of course, the means are probably different. By random chance, any two groups should be at least a little bit different. But is this difference only because of that random chance I just mentioned? Or is it because the laser surgery actually reduces recovery time? That's what you'd be testing here. Seeking a relationship, that's often something that in healthcare you call looking for risk factors. That's the other kind of test you might be doing. Does the concentration of an antigen in a new mother's blood predict or in some way correspond to the concentration of the antigen in her newborn's blood? Does a woman's bone density depend on her age? Is there a trend to be found between these two sets of data, either an upward trend or downward? So now, having answered all of the questions, I have my data broken up into its different categories. If you've answered all three of the small questions, you should know which test to use. Each test falls into a different block based on the answers to the three questions that we asked. If we're comparing, and we have quantitative data, we're probably comparing the means of data values. We do this with what's called a t-test. Or when we have three or more groups, we call the test analysis of variance, or ANOVA for short. But you can think of ANOVA sort of as a many-sample t-test. When we're looking for that relationship, for a trend between two sets of data, that's called correlation and regression. We're not dealing with means at all, but how the two data values that correspond to the natural pairing line up. But you'll notice there's still one block that has two different tests you might be using. Let's talk about a two-sample t versus a paired t test. So we have quantitative data, we have two samples, but it's really two samples special. Most likely it's one sample of people, but we've taken two measurements of the same kind. When I say the same kind, I mean they're the same measurement maybe at different times or on different parts of the body, but it's two body weights or two different systolic blood pressures. Okay? We want to compare the sets of data, but the question is, do we just want to know if they're the same or not, or are we asking how they changed? How big a difference are we talking about? A two-sample t ignores the fact that there's any connection between the two samples. It just treats it like it would any two sets of data, even if they came from completely separate groups. A paired t-test really looks at the difference. And here, I don't mean the general English word difference. I specifically mean difference as in the result of subtracting two sets of data. Remember how a sum is what you get when you add two things, and a difference is what you get when you subtract two things? Well, here we're talking about subtracting two things. A paired t-test is incredibly common for use for before and after data. I weigh people, put them on a diet, and then weigh them again a month later. I want to know more than just are the mean weights different. I want to know if, on average, the weight for each person went down. So I'm not just comparing a bunch of weights to a bunch of weights. I'm comparing the weight change of subject 1 and subject 2 and subject 3 and subject 4 and looking at the average, the mean weight change of each individual person. I'm using the fact that it's paired data, that each after weight corresponds to a before weight for the same person. So here we have it, our list divided by the questions. You can see I've labeled question 1, question 2, and question 3. When you are trying to figure out what test you're going to use when you're designing a study, ask yourself the 3 questions. Question 1, will I be collecting categorical or quantitative data? And remember, if you're counting how many subjects have a particular trait, that's categorical. Question 2, am I collecting data from only one sample, or from 2 samples, or from 3 or more samples? Or maybe I have 2 sets of data that come from one set of people. And finally, question 3, am I trying to compare my data from each group, or from my one group to a historic or global value? Or am I looking for a relationship between my 2 sets of data? If you answer those 3 questions, I bet you'll know which data set to use.